Oh. Welcome to. Oh man. Hold on one second. Let me. Sorry, I had to sort of mess around. We'll just put this. Let's hide this for now. Okay, there we go. All right. So, I think we'll also just. You know what I meant to do? Make ourselves a little bit smaller. There we go. All right. So I meant to fix the size of the Ruing Baron on this one, and I forgot. Too many other things going on in my head. Okay, anyway. So I will give some people a little bit of time to sort of straggle on in. Today, you are all part of my experiment. By which I mean that I have a paper that I need to try and extract some specific info out of. And so we all together get to look at this and scratch our heads and be like, what the heck is going on here? So it's going to be fun. This is going to be a pretty math heavy one. I will not know all the math. We might go back and forth and do some... have to do some searches and go onto some Googling and all that jazz. All that jazz. Yeah, so a little bit different from yesterday's impromptu stream of Battlefield 4 with B there. That was a lot of fun, but hold on a sec. I gotta voop. What's whooping? What's whooping? My phone's whooping. Literally nothing useful. Okay, cool. Good job, phone. I know I could count on you for something. Okay, anyway. Yeah, so this will be a little bit different in tone from from our time that we had yesterday. So, however, that being said, I'm trying to work out the best way to include more of those types of streams because I don't know about you guys, but I had a lot of fun. It's been a while since B and I sort of played Battlefield 4 together, and I forgot how much shenanigans we get up to when we do that. So I'm going to try and figure out how to get that fixed regularly in the schedule because I think that'll be fun. Yeah, that'll be fun. Fun. Excellent. All right. So, in the meantime, for today, like I said, I understand if you kind of came in yesterday and that was your first exposure to me. If you see today and you're like, oh my God, what the heck did I walk into? If this isn't your cup of tea, that's perfectly fine. The goal is to have this open to all interests. So as many people as possible that might be interested in this. So, today, as I said, I am recruiting all of you for assistance. Let's see here. Boop, 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 boop. Let's see our... There we go. See, I'm still ruined behind it. All right. I think we just make ourselves smaller. Okay, that works. Excellent. So, today for something completely different, we're looking at this paper, and I will explain to you exactly why we're looking at this paper in a moment, but towards a better understanding of gradient-based attribution method for deep neural networks. Am I doing anything with deep neural networks? No, we're not doing anything with deep neural networks. However, we are interested in the following. We are doing a little bit of an attribution thing. So for some of the research I'm working on, we're doing a little bit of an attribution thing where we have daily information And this is all, signal loss information, daily signal. It doesn't really matter specifically what it is. And then we have a whole bunch of environmental influences. They're each affecting how these days work, right? And so the goal is to figure out which of these do we actually care about, which can we sort of safely ignore within, certain error bounds, right? Ideally, you would take all of the possible influences into account, but that's just not possible, right? We want to make a relatively simple model so we can estimate what the next day looks like based on our knowledge of current environmental conditions, right? So that is kind of the goal of this whole thing. As part of it, we've done one of the methods that we've used to evaluate this is called SHAP, which is shapely. I think the definition's in here. Anyway, it's just a method of determining which influence is most important for different things. So we kind of have a SHAP value for that correlates to each of these, and that value is theoretically saying how important each of these influences are on the local movement within each day, right? As it goes through the day, and then it gives sort of an overall SHAP value. What we want to do, right, is for our we want so there's a couple ways you can make this model, right? So I'm just gonna go over here, right? Keep going. There we go. Right. So there's a few ways we can make a model. We could say, all right, so our loss for today, right? So let's call it, we can do it a little bit bigger than that. Like this. Right, so our loss as a function of, so our loss is going to be influenced by all of these environmental factors, right? So this is daily loss. I'm actually looking at a couple of key points during the day, and I'm using that to make an estimate, but don't worry about it. And then this is influenced by some list of environmental factors, right? So this is E and V factors. And so these might be E equals F10.7, which is like a metric of how intense the solar radiation is. Or it could be AP, which is a measure of the geomagnetic field and how strong that is, or blah, 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 right? There's this whole slew of these things. So that's E, right? So E is just sort of the set of possible influences, right? And so we could say, all right, well, we'll start with some initial guess, right? And we'll say this is sort of what we expect it to do. And then it'll have some error factor that's sort of the sum of all these influences. So let's say there are, this is I long, right? So that's sum overall over I of alpha I EI, right? So I can say it like this. So I'm gonna sort of get some coefficient for each of these factors, and that'll sort of map all of the factors into my total loss, so that when I sum them up, I get some total loss value. I can add that to my default, which can be really whatever I want. Like I could set the default to zeros, in which case this would just be the entirety of the set, or I could do some other thing. It doesn't really matter. All that's going to do is affect what these values of alpha are, right? So these values of alpha are sort of empirically found, right? They're fit values, so they're not really, you're not there's a lot of stuff that's going into this, right? So buried within alpha. So for example, alpha F10.7 is going to include all the reasons increase or the value, I should say. So this can be all the reasons the value of F10.7, which again is a metric of how intense the solar radiation is, affects loss. And there's a lot of physics going in there behind the scenes, right? And it's all sort of hidden in terms of this fit value. Since we have a whole bunch of data that we can generate these fit values for, we can just sort of say, yeah, there's a bunch of stuff going on, but, you know, for this little model, we're going to ignore that for now, and we're just going to assume that there's some fit value that's good enough to estimate it based on the value of F10.7. So I multiply that alpha by the value of F10.7, and I add up all of these across the whole list to E, and that's my error change. And so that's sort of the first a first order approximation that you can sort of do. But we want it to be a little bit better than that. And so what we can do is we can add something else to it, right? Plus another fit value, right? And now we want DL DEI times well, we'll worry about that this piece. There's something else over here. I'm not going to worry about it because conceptually, it's not as important right now. So what have we done now? We've added something different. We've added another fit parameter, right? Which again is influence this. And now we've asked not just, how does the value of the environmental influence affect my loss, but what's the rate of change, right? This is the derivative. So what's the rate of change of my loss as I change that value, right? So if I keep everything else constant and I just shift this value around, what's the rate of change of loss around that point that I'm looking at? So this will give me the local gradient, right? The local rate of change with respect to each of these. And again, I can sum these up. And so this is going to be slightly more accurate because it's not just talking about the loss, but it's also taking into account the sort of the local stability of that loss, right? So how fast is it changing? So now, because of that, I can make a slightly better estimate. If you've heard this term, you can think of this as a Taylor series, which is kind of what it is, right? This is a Taylor expansion. And so, essentially, this is like the first two elements of a Taylor series expansion. But yeah, so that's what we want to do, right? We want to build this little model up, and so that's part of the research piece. We want to find what these alphas and betas are, but there's something else a little wonky, which is that we don't really have. We could do approximations of what DLDE looks like, but that's going to be kind of difficult because we just have day one looks like this, the loss looks like this, day two, the loss looks like this, day three, the loss looks like this, right? So this is all we have. And now we have, our E values that are correlated with each of these days, but I don't really have isolated sort of methods to build up this DLDE for each of these influences. However, I have been given to understand, based on some other stuff, that we can sort of estimate what this is from the importance parameters that we built up. Either through SHAP or through some other mechanism. So all of that introduction to say, somewhere buried in this silly paper are a couple of things that we can hopefully kind of estimate as well, this is analogous to what we're looking for. So we can pull out this method, right, and take a look at it. Obviously, this paper is looking at neural networks and trying to, so AI neural networks, specifically deep neural networks, where you have all of these different layers and there's all these like interconnected neuron things, right? And so you end up with this huge interconnected map of shenanigans, and you have your input, and each of these is doing some sort of math on your input, and then there's an output. These are how like the large language models all work, and knowing what's going on in here is kind of impossible, right, as it's doing these, because each of these layers is essentially a giant set of fit parameters, based on all of the data that they've used to build this learning model, right? So each of these is individually tuned. There's literally millions of different parameters per level that are individually tuned to provide specific outputs for specific inputs. And that's how all of these large language models work. But trying to figure out what's going on in here is a hard problem, because there's a lot of complexity that's sort of built into here, and they're so big that humans aren't making these connections anymore, right? These connections are being autonomously grown, essentially. You can think of them like neural connections that are grown based on influences, right? So like a child learns learns something, and that's, or a child, anyone learns something, right? And that's mirrored in the neural interconnections in the brain, but you're not going through and like specifically moving this neural connection to that nerve and this one to that nerve, right? You're just looking at this like higher emergent level. So, knowing what's going on with each specific neuron moving, connecting to each other neuron is just an impossible task for us. Anyway, so that's the correlation here. So what we're going to do is we're going to sort of skim this, because again, we're not going deep into the specifics of the neural network piece. Like, that's not our cup of tea. We're trying to pull out anything potentially useful from this. So, coffee. Sorry. Okay. So let's start reading. While DNNs have had a large impact on a variety of different tasks, blah, 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 explaining the predictions is still challenging, right? In advance, until you put this input in, you don't really know what this output's going to look like. All right. The lack of tools to inspect the behavior of these black box models makes DNNs less trustable for domains where interpretability and reliability are crucial, right? Because since you don't actually know what processing is going on, how do you know that you can trust the output? Of course, you can't always trust the output, but that's, DNNs can make all kinds of silly interconnections that don't actually make sense or aren't correlated to reality. We see this all the time. In this work, we study the problem of assigning an attribution value, which again is similar to what we were trying to do, right? We're trying to assign an attribution value to the change of our loss by each of those environmental factors, sometimes called relevance or contribution to each of the input feature of a network. More formally, the DNN that takes in some input X, right, where X is just some set of real number values, and produces an output S of X, where S is just some function on each of those values, where C is the total number of output neurons, right? So there are C different functions essentially that are each being applied onto this. Given, right, because X is really right, each of these functions is operating on the entirety of X, right, because X is kind of a vector, right? So each of these is functions is operating on X. First this one, and then this one, and then this one, and each of them is different. All right. Blah, 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 blah. Given a specific target neuron C, the goal of an attribution method is to determine the contribution RC for RC 1 to n of Rn. Okay, for each input of X to the output SC. So what they want to do is they want to say, I've got this vector that I'm submitting into this neural structure S1 of X, right? So this is X. And then it's going to give me some output Y, whatever, this is going to do something on this input to each value of the input, and it's going to return some output that's different than the input. Right. And so we want to know, how much does this matter to this or to this? You know, how much do each of these input pieces affect what S is actually doing, since we can't really see what S is. We don't know what S is, but we want to know how much of this really matters. Can we, for example, right, you're always trying to minimize the amount of computation you have to do. So can we make some version of X that's smaller because some of these values don't really matter? I don't know. It's, so same thing with my my model that I'm trying to build. The fewer environmental conditions I need to know to estimate what a day of loss is going to be, the better, right? I don't want to have to input all of this kind of data that are, you know, some of it's from measurements, some of it's from simulation, and I have to take all these and put them into my model. The fewer of those I have, the better, right? Because the easier it is to use. So ideally, I want to know which of these elements of X actually matter to Y, so that I can just take those and I can ignore the rest of them, right? And then I could say, well, if I ignore this, you know, this many values of X, if these I say don't matter, here's the error that's going to happen because of that, right? Or if I need like a more precision, maybe I'll take this one, right? And I'll add this other one in. That'll decrease my error by a certain amount in Y, all these kinds of things, right? So that's part of what we're trying to do. And that's why this, you know, what they're doing here sort of maps to what we're doing. Okay, so they're trying to find the attribution R for each value of X, right? For a classification task, target neuron interest is usually the output neuron assigned with the correct class for a given sample. So in other words, where it's the goal of it is to say, this is a blank, right? I think they have a picture of a snake later, right? So it's like this picture, you give the model a picture of a snake, and the model successfully says this picture is a snake. So try establishing a pattern of element values so the pattern is a cleaner sum of multiple details. Yeah, so all of these are approximations anyway, right? So what you're going to do is you're going to essentially build up the models with in different ways, and you're going to look at how effective those models are at estimating certain days, right? So I have years worth of data, right? The different days of data. So what I'm going to do is I take some of those out and say, this is going to be my validation pieces, right? These aren't going to go into building the model. I build the model with the rest of the days, and then I use that model to estimate the days that I've extracted, right? Usually about 20%. So I then apply the model I've built onto my validation days and ask, what's my error? And then I can take, like, you know, the mean of that error or the median of that error and say, okay, well, you should expect about this much error if you use blah, blah, blah for your model, right? If you use these these inputs for your model. And then what I can do is with different number of inputs, I can see how the error changes with the number of inputs. And I could say, well, it depends how much you care about, right? If you are fine with being plus or minus 5 dB in your signal loss, great, you only need this many things. If you really care about being plus or minus 2 dB, well, then you're going to need this many of you're going to have to take into account all of these other things that, even though they have smaller influences, will still add up to a larger error. That's the target that we're trying to do with this. Okay. Let me see. Where does this? Okay, we're almost. All right. Okay. Blah, 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 blah. When the attributions of all input features are arranged together to have the same shape of the input sample, we talk about attribution masks. Figure 1.2 or 1-2. Where's figure 1-2? Figure 1. I don't know. We'll find figures as we find them, I guess. Let me make sure. Okay. All right. So in other words, right. So the attribution maps are essentially mapping how much each of these values matters. We got a wee woo outside. I knew it. Let's see. You can go right by the. Yep. There's the ambulance. Okay. Okay. Which usually, all right. So that generates these heat maps, right? Which is how much of, right? You can map, especially if your input. So I'm doing a relatively simple task where I just have a single dimensional input, but my input could be 2-dimensional. For example, if I have a picture, right? And so I want to know how much the value of this pixel matters compared to the value of this pixel if I'm trying to estimate what this is a picture of, right? So now I might have a 2-dimensional input array. So X is not just a single dimension, it's a 2-dimensional thing. And now I can do this little heat map of how much each of these pixels matters, which again, if I care about minimizing the amount of information I need to give into this, maybe I can take only a few pixels and still get the correct answer out. Right? That's the question. Okay. Where red color indicates features contribute positively to the activation of the target output, blue colors indicate features have a suppressing effect on it. So you might have noise within this picture, and some of this noise is actually detrimental to your thing, right? So you might, before you hand off the picture, you might want to do some sort of denoising to kind of reduce the elements of the picture that are causing problems for, in this case, your neural network to actually identify what it is. Okay. The problem is finding attributions for deep neural networks. The problem of finding has been tackled by several previous works, blah, 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 blah. Unfortunately, due to slightly different problem formulation, lack of compatibility with a variety of existing DNN architectures, no common benchmark or comprehensive comparison variable. In other words, so people have clearly tried this before, but while there are these categories of things called deep neural networks, they're all kind of different, and so none of these methods really apply across all the different types of deep neural networks. So they're going to say, here's how you apply it to all of them, is my guess of what they're going to do. Anyway, various new attribution methods have been published in the last few years, but we believe a better theoretical understanding of their properties is fundamental. The contribution to this work is twofold. We provide that epsilon LRP and deep lift can be reformulated as computing back propagation for a modified gradient function. So this gradient element is going to be important, I think, right? Because that gradient is, what is a gradient, right? A gradient is saying how much something is changing. grad f. No, I'm sorry. That's div x. I'm sorry, grad. I know my math. Hold on. I'm being stupid. All right. Grad f is equal to, so if f is a three-dimensional, right? If f is x, y, z. Dang it. I was in the middle trying to explain something. xy, right? If I have some function of xyz, the gradient of f is df dx in the x direction plus df dy in the y direction plus df dz in the z direction, which is telling me how f is changing with x as you move in the x direction, how f is changing with y as you move in the y direction, and how f is changing with z as you move in the z direction, which, if you remember, is exactly the kind of thing that we were trying to find as part of our second part of our model, right? The that second order influence on our model. So that's what initially kind of caught me about this paper and why I wanted to go through it. All right. Coffee. Okay, let's construct it. Okay. This allows the contribution of a unified framework that comprises several gradient-based attribution methods. So there are several different ways you could do it. So, which reveals how these methods are strongly related, if not equivalent, under certain conditions. Okay, so if we select a method, so this is important, right? We're going to have to see what those conditions are. And if they do or do not apply to our actual thing that we're looking at, right? We also show how this formulation enables a more convenient implementation with modern graph. Okay, blah, 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 blah. We introduce a definition of sensitivity n, which generalizes properties of completeness and summation to delta. Hopefully they'll explain what that is, because I don't want to have to dive into this paper as well. And we will compare several methods against this metric on widely adopted data sets and architecture, blah, blah, blah. That's what they're doing. Okay, cool. Is that telling us what you're going to do? Actually do it. Okay, let's see. Good. There we are. Perturbation-based methods. Perturbation-based methods are directly compute the attribution of an input feature or set of features by removing, masking, or altering them, and running a forward pass on the new input, measuring the difference with the original output. Right. So this is kind of what I've done. So a lot of the feature modeling, what it'll do is it'll say, all right, if I'm looking at, right, S of X equals Y, and what I'll do is I'll perturb some part, right? I'll take this as my initial. This is my zero function. I'll have a Y naught. Then I'll perturb the first of these elements and look at what that does to Y, right? Then I'll perturb the second of these elements and I'll look at what that does to Y. And I'll do it each by different amounts, and I'll get this whole combinatorics thing. And so then I'll use that to say, well, if I change the first one in this way, then I know that my Y is going to change in that way, right? So that's sort of it's kind of a brute calculation approach, but it is a way that's often used for these sorts of things. Okay. This technique has been applied to convolutional neural networks in the domain of image classification by these guys, visualizing the probability of the correct class as a function of the position of a gray patch occluding part of the image. So they had their image, right? And they moved this patch around the image. So they're blocking out part of the image and they're moving this around. And they're saying, all right, how much does this section of the image affect the output of the classifier? While perturbation-based methods allow a direct estimation of the marginal effect of a feature, they tend to be very slow as the number of features to test grows, i.e. up to hours for a single image. What's more, given the nonlinear nature of DNNs, the result is strongly influenced by a number of features that are removed altogether from each iteration. Yeah, so I understand why they were doing that. I don't. You kind of have to do that per image, and you're running it multiple times. That's kind of a silly way to do it, to my mind. Anyway, in the remainder of the paper, we'll consider the occluding method as a comparison benchmark for other perturbation methods. We'll use this method referred to as occlusion 1, replacing one feature xi at a time with 0, and measuring the effect of the perturbation on the target, right? So I'm going to look at my output, and I'll subtract off the output with one of my xi values in my little vector being 0, right? And then I'll subtract that, and I'll get some error, which is kind of what we're doing with our model. That's why this paper is interesting. Where we're having our initial, and then we have some error that's connected to it, right? Where we use xi equals new to indicate a sample of x within the real numbers whose ith component has been replaced with new. Okay, so in other words, you're replacing some ith value with new. Sure. The choice of 0 as a baseline is consistent with related literature. Okay, so new just happens to be 0. This entire thing is unnecessary. Don't need that anyway. All right, attributions generalized by occluding parts of the image with squared gray patch. All right, so this is that output of that method that we're talking about, where they took a square gray patch and they moved it around the image, and they tried to see how much each of these areas mattered to the value of the output, right? How correct the output, whether the output was correct or not. And these are different sizes of the gray patch. So I presume this is just a 1 pixel, 5 by 5 pixels, 10 by 10 pixels, and 15 by 15 pixels is my guess as to what that is. Okay, notice how the size of the patch influenced the result with the focus on the main subject only when using bigger patches. This is kind of what I was thinking earlier, where it's like, right, so much matters with what you select your patch being. What if I took a non-square shape? I might find other pieces influence things. I don't know. This doesn't seem like a good method to me, but I don't know much, so I'm just spitballing based on my knowledge, which is not about convolutional neural networks, because that is not my area of expertise by a large margin. Okay. So, backpropagation based methods compute the attribution for all input features in a single forwards and backwards path through the networks. Sometimes several of these steps are necessary, but the number does not depend on the number of input features, generally much smaller than for perturbation-based methods. While these methods are generally faster than perturbation methods, their outcome can hardly be directly related to a variation of the output. So I'm not really... Okay, so backpropagation-based methods compute the attributes for all input features in a single forward and back pass through the network. What do they mean by a back pass? Does that mean they reverse the network itself? Or does that mean they take the output and push the output through the network? I'm not sure what exactly that means. We'll see if we can figure that out as we go. All right. So these are the different methods that were used to do this backpropagation thingy. Words are hard. Yeah. So these are different ways of trying to do that. Okay. So the first of these, gradient star. You'll have to. Oh, jeez, did not mean to do that. All right. All right. Gradient star. Okay, it was first proposed as a technique to improve the sharpness of the attribution maps. The attribution is computed taking the signed partial derivatives of the output with respect to the input and multiplying them by the input itself. Refer to table 1 for the mathematical definition. So sometimes it helps to just see the math. Where's table 1? Where's table 1? Where's table 1? There's table 1. All right. Table 1. Let's just take a look at this. All right. So, what are they looking at with this first one? Let's break this apart, right? The change in the output as a function of the entirety of x with how each individual value of x changes multiplied by that value. This is fairly, I mean, this is pretty standard, right? This is telling you in the local, this is kind of what I was talking about before, right? In the local area of x being equal to xi, right? No. Xi is the specific value in the x1, x2, right? So I'm rather cross out what I just said because I was wrong. I'm taking each of these parts of the input vector and I'm multiplying it by the gradient of how the output changes if I only change that vector, right? So I'm essentially modifying each of these by that, and that's how I'm defining the attribution. All right. I wish table 1 was closer to where he's defining these. That would make life a little easier. Anyway. Can you see that well? All right. Integrated gradient. Similarly to gradient star output, computes the partial derivative of the output with respect to each input feature. However, while the gradient star input computes a single derivative evaluated at provided input x, integrated gradients compute the average gradient while the inputs vary along a linear path from some baseline x bar to x. Baseline is defined by the user and chosen to be 0. We report the mathematical definition in table 1. Integrated gradients satisfy a notable property. The attribution sums up to the target output minus the target output evaluated at the baseline. Mathematically, it's that. In related literature, this property has been variously called completeness, summation to delta, or efficiency. So that's what summation to delta is. In the context of cooperative game theory, is often recognized as desirable for attribution methods. Okay, so what is it saying? Right. So we are so first off, this property here, right? What this is saying is I'm using this method to generate each of these RC1, RC2, right? So this is what I'm using the method to generate, right? This is what I'm generating with the method. And I'm saying that that is equal to the output of some vector, the output applied to some vector x minus the output applied to my, I'm just going to use not instead of bar because I'm using the vector there, right? So what I'm doing is I'm generating this through some integration between x, what was it? x naught and x, right? So I'm using these as my integration bounds. And it turns out if I do that, then my my attribution is equivalent to just literally the subtraction between the if I go from my naught point to my other point that I'm looking at. So again, if we go down to that table, I can get there. I believe this is table. Yep. All right. So how are we doing it? So again, my x is my perturbed x, right? So I've changed something in again. What we're trying to do, trying to say, I have some baseline value, and I'm trying to ask what my error is, how much the error is influenced by each specific change in x within each element of x, right? So I look at the difference between my value of x and my whatever baseline I'm using. And then I'm going to integrate. So I'm going to take this same derivative, right? This is the same derivative, but then I'm going to integrate over alpha, where alpha is x bar minus delta x. Let me see. What does this mean? X bar minus delta x. So x tilde is x bar plus alpha minus alpha, right? So if that's 0, it'd be alpha. It'd be 0 plus alpha x, so alpha goes from 0 to 1. Okay. At so just thinking through what this looks like, imagine x bar is 0, right? So we're going from alpha equals 0, so x is x bar, to alpha is 1, in which case you have x minus 0. So it would just be to x, right? Alpha is going from, so that means this is going from 0 to x. So yeah, by taking this difference here, and then you're just multiplying it by a constant that's your integration constant. That it's going from 0 to 1. So at 0, obviously this has no influence, and then at 1, this has complete influence over it. So that's looking at, let's see, and then here's x, right? So I am taking, if this is delta x, so I'm looking at x bar plus delta x, and then I am integrating. Okay, yeah. Okay. Took me a second to. Sorry, sometimes it takes a second for me to figure out exactly what's going on. So I apologize. So now I can explain it, I think. So what we're doing is we're looking at I perturb, right? So again, what are we doing? We're taking some xi, right? So this is, we're gonna say x naught, xi naught, or x1 naught, x2 naught, blah blah blah, right? Xi naught. Or I guess xn. Right. So we're taking this, and we say that this we're gonna change to x, right? So now we're gonna take, what are we gonna do? We're gonna take x1 naught, and we're gonna change it to x1 not, right? And we're gonna take x2 not and change it to x2, right? So we're gonna shift this over to this by shifting the specific elements in certain ways. And maybe I'll just change one element, maybe I'll change all the elements. But what I'm looking at is how does my output change as I change with respect to each one, right? So what I'm looking at is for each of these, right, I'm going to take, say, this slice here. I'm going to say I'm looking at the difference between x1 not and x1, right? So it's going to be delta x, I guess delta x1. I'm not explaining this very easily. Is x1 not minus x1, right? So I'm taking the initial, I'm subtracting the other one off of it. This is my delta x. So that's true for each of the elements in the vector, right? And that's what this is. Or I'm reverse it, right? I'm taking the new minus the original, whatever you want to do. And then I'm multiplying that by how this is changing, right? The rate of change of this in the same way that we did before, we talked about before with how you're talking about the rate of change, right? ds dxi. But then we're multiplying this, or we're integrating this times alpha delta x. So we're saying it's delta x times this whole jazz. And alpha is going to between 0 and 1. So is that a plus or is that multiplied by? Actually, it's a good question. It's not. It's, I'm sorry. We're doing this for x equals alpha delta x. There we go. Yeah. So I because each individual one, right? So that's how we're doing it. So it's the change in each of these values going from the initial to the new one times the integral of how the rate of change going from the initial to the final. Let's see. Can I draw this out in a way that actually makes sense for everyone? Imagine, right, my value that I'm looking at is here and is going from here to here. Let's do this in a way that we could see. Okay. It's going like to there, right? And it's going to end there. This is my this is the way in which my value xi changes, right? So what I'm going to do is I'm going to take the derivative of this. So I'm going to take the rate of change of this at each of these points, right? So I'm going to take, so I'm going to look at what the rate of change is at each of these points, right? So again, this is the slope of this, right? It's the derivative of it. It's the rate of change of it at each of these points. And I'm going to integrate so I'm essentially going to add up all of these rate of changes from the beginning to the end, right? So I'm getting the rate of change at each of these points, and I'm adding up the rate of change from the start to the end. And I'm going to say that is now my value that I'm multiplying by the actual, right? This is delta x. So I'm multiplying this value of delta x by the rate of change as integrated over, oh, geez, you can't see the diagram. Thank you. There it is. I forget that, right. So let me go through this again. This is my difference, my delta x, right, is between here and here. What I'm going to do is I'm going to look at how S is changing, the rate of change at each point. And then I'm going to add up all of these rates of change. And so what that does is that gives me an average rate of change over this whole thing, right? And I'm going to multiply delta x by the average rate of change over this path. So then I can kind of ignore some of these things. I can just look at this mean rate of change. And I'm going to do that through this integral method. I hope that made something close to sense. I don't know if that did, but I hope that... Oh, man, I need more coffee. All right. Excellent. Okay, so that's what this method is. Ooh, and again, each of these, what this is outputting is... Let me get back up to it. Let me get back up to it. Can we see it on here? Yep, okay. So again, the delta x times the mean of x x prime, right? Or sorry, it's not that. It's times the mean of s prime, right? The average of s prime of x is essentially what you're looking at, right? So this is giving you your metric of how much it matters to the output. How much does each of these individual ones, how much does that matter to the output of the thing, right? So that is another way of doing it. So that might be... It'll be curious to see if that's useful, right? So if I'm thinking of my problem, right? My output is the loss measure, right? The measured loss. So my S of x is the loss value that I measure on day whatever, day n, right? That's kind of my output. My input is the environmental conditions like F10.7, right? AP, blah, 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 blah. So what I would have to do, and this is where I'm not sure if this is doable because I don't have continuous values. I just have a series of these things, right? I would want to know the mean rate of change of L for, say, AP goes from the min to the max. But I might not have enough values to be able to estimate all of these. So I might just have to take the values that I have that correlate to the specific days that I have available. And granted, I have a lot of days available, so I have fairly good granularity on this. So I might be able to apply this. I'm not sure. I might have to try and see if that is if that integrated gradient is something that we can do. Because the fact that we can say it's got this mathematical completeness, which apparently is a desirable part of attribution, maybe this will be how I do that part of the question. I'll have to figure it out. Anyway, so that's why this paper is useful, right? Because I'm trying to go and connect the different elements of this paper into what I'm doing, right? Okay, layer-wise relevance propagation, or LRP, is computed with a backwards pass on the network. Let us consider some quantity RIL called relevance of unit I of layer L. Let me read this through and then I'll try and explain as I understand it, and then please feel free to push back if that's not making sense. The algorithm starts at the output layer L and assigns the relevance of the target neuron C equal to the output of the neuron itself, and the relevance to all other neurons equal to 0. The algorithm proceeds layer to layer. So this actually, I don't think we care about. I don't think we need to care about this one, because this is really mattering for a series of neural connections, right? And then it's looking at the next layer of neural connections. Right. And so it's looking at how each of these, but we're really only doing one step, right? And that's why our problem is kind of an order of magnitude less complex than this, in that we're only really doing one step. We're not really doing all of these built-in internal steps. So I think we don't need to worry about that unless we did like a single step version of this. But the algorithm runs layer by layer. Okay. Redistribution the prediction score SI until the input layer is reached. One recursive rule for the redistribution of a layer's relevance to the following layer is the epsilon rule described in equation 2. So RL of I is the target. A small quantity epsilon is added to the denominator equation 2 to avoid numerical instabilities. Okay. This seems fairly complex, and I don't think we need to get into it. I could be wrong on that, but I don't think. So we're not using a deep neural net, right? We're not doing a whole different series of learning steps. We're just sort of making one estimation. So that's why I think the multiple layers that you have in a deep neural net don't really matter to us. We essentially have a single input-output. We're not really doing a multi-step process. So that's why I don't think this applies, right? They're trying to look at this series of functions that are being applied at each, right? So the output of the first function, right? This becomes S1 of X, and then you get to the second layer, and this becomes S2 of S1 of X, right? And you end up with this iterated methodology that's going through all the layers, right? So you're trying to back propagate the layers to uncover what each of these pieces is and how much the input matters to each of these, and how the input, a deviation on my input X is going to propagate through all of these different S's, right? That's the multi-layer thing that they're going for in here. I don't think we really care about that, because we're just saying, I don't think we're doing this multi-step shenanigans. And so that's why I don't think the layers aspect applies to our problem set. Again, this paper is sort of analogically related, right? It's not really directly related in the same way. I just realized I didn't announce to my server that I was going live. I'm a moron. Anyway, I'm a bad streamer. Sorry. I don't know why that popped in my head. So then we'll see what their method is. Okay. And finally, we have deep lift. Okay. Proceeds in a backwards fashion similar to LRP. Each unit I is assigned an attribution that represents the relative effect of the unit activated at the original network input X compared to the activation of some reference X bar. Okay, so it's similar kind of thing that we're talking about here. We're comparing the output to the output at some reference point. Reference values Z, J, I for all hidden units are determined running a forward pass to the network, right? So you run a forward pass to the network, and you get your reference values for all hidden units are determined running a forward pass to right, using the baseline as the input and recording the activation of each unit as LRP. The baseline is often chosen to be 0. The relevance propagation is described in equation 4. Okay, so let's see. Okay, the reference values Zij for all hidden units. Okay, so that's right, because the hidden units are all of these extra layers, right? You don't actually see what these layers are doing. All you know is the input and the output. So these are all technically hidden layers. As an LRP, the baseline is often chosen. Okay. The attribution at the input layer are defined as that as for LRP. Okay, so I think this is another multi-layer thing, right? For the weighted activation of neuron I into neuron J or the baseline X. Yeah, so this is another method that I don't think we need to really care about, right? As for integrated deep lift, it was designed to satisfy completeness. The rule, okay. Okay, so this is a completeness method mechanism that requires the multi-level thing. You can't use layers with different interface elements taken into account in one time moment. I mean, so it's not necessarily time, right? It's just kind of order of operations. Functionally, that can be time, but your input could be, right? My input could be a picture where one of my dimensions is the X or the Y of the picture, or my input dimensions could be, for mine, right? I'm looking at loss values. The loss values are days and hours of the day. So both of my input dimensions are time, but different layers of time, right? Because this is giving me measurements at each hour, and this is different days, day 1, day 2, day 3. So using time is a little wonky because it's a physical input. This is a sort of mathematical process. My input variables could be almost anything, right? Can't use layers with different interface elements taken into account in one time moment. Interference elements. So what are you meaning by the interference elements? So elements taken into account in one time moment. Each of them is going to have a different, right? If I go from a layer in regards to the losses of your prediction elements, so yeah, kind of, yes, right? So each of these layers you can think of as applying to all of the. I have a little spider on my thing here. I think I see what you're saying. So each of this is going to depend on all of the elements E1, E2, E3, right? That these are all daily measurements of different elements of this, right? And these are all gonna each affect the output value. So you're kind of computing these all at once. Or rather, I should say, the output value that I'm getting, right? So this L value that I already have recorded, right? This is just a measured value, is kind of taking into account the computation of all of these at once. And that's part of the problem. All of these are sort of mixed together. The influence of all of these is mixed together. And so you're trying to pick out what the influences of all of these are so that you can independently guess what the output's going to be if I only have changed E2 or I only have changed E3. So how does E2 affect my prediction? How does E3 affect my prediction, right? That's what I really care about, because I know that, or it might even be, there might be even be an interrelation between E1 and E2, right? So these might influence each other. So this is part of the issue. So for example, right, I'm looking at my solar wind. Solar wind is some of these, are this metrics of the solar wind are a part of this. Well, that solar wind is also going to affect my geomagnetic strength, right? And so that means that all of a sudden these aren't independent variables, right? My geomagnetic strength is going to be dependent in some way on the solar wind. My solar wind is going to be in some way dependent on my solar radiance output, right? These things aren't really independent values, but we're sort of trying to hope that the interrelation between them is such that we can still capture it in our little model here. So we're kind of playing that game. There's also, to add complexity to this, there are other influences to these losses that I'm not taking into account, right? So I'm looking at what I really have is I have 3 receivers, right? 2 of them are close together and one's far apart, right? And the distance, so if here's my transmitter, this difference matters. Because this is going to determine how long I'm in the lossy layer of the ionosphere and how much additional loss I'm going to get from my propagation loss. Not only does that matter, but my frequency matters, right? So my baseline frequency is 2.5 megahertz at each of these. I have other frequencies that I've collected, but I'm just right now looking at 2.5. I did not mean to do it. Oh God, where'd it go? It's up here somewhere. Right? Well, the frequency that I'm looking at is also going to affect what my loss looks like, because it's going to affect how each of these matter to the loss, right? Because the loss is going to be proportional to, or is going to be related to my index of refraction from going through the ions in the ionosphere, right? The electrons and the ions in the ionosphere. But this is a function of frequency. So my loss is proportional to my frequency, or is related to my frequency. My loss is also related to my distance of propagation, and it's also related to all of these environmental factors. So the hope is, by essentially building this model that we talked about up here, right? If I build a per frequency, per location model here, I can then use that as my baseline to start permuting frequency and to start permuting location, right? So if I then start permuting the frequency at each of these locations, and I see how that affects the model, right? Specifically, it's going to affect these alpha and beta parameters. I can then theoretically build my second level, a second level model saying, well, it's actually alpha I is a function of frequency and beta I is a function of, you can't actually see that. Beta I is a function of frequency, right? This is my level 2 version, right? The other one was my level 1. This is my level 2. I'm going to say, okay, I have alpha I and as a function of frequency, beta I as a function of frequency. Then my level 3, which is going to be all right, level 2 should be doable. Level 3 is going to be a little bit difficult because I only have these 3 locations, but ideally my level 3 is going to be alpha I as a function of frequency and location, and beta I, actually not location, I'm sorry. Let me take that back. It's going to be a function of distance. And beta I is a function of frequency and distance, right? Where my distance is transmitter to receiver distance, right? So here's my TX, here's my RX, and I'm doing this number with my signal. I'm bouncing it off, right? So this is my D here. So I'm going to have alpha for each of these environmental factors is going to be a function of frequency and distance. That's my final model, right? Because now that tells me I can plug in a frequency that I care about. I can plug in a distance between my transmitter and my receiver. I can plug in and I can use those to get alpha and beta for all of my environmental measurements. I plug in my environmental measurements into this function, and I can estimate what my loss is going to be at a location, at a frequency, given the environmental conditions that I have. So that's the end target, right? That's the end model that we're trying to get to. But right now we're trying to build a frequency. We're trying to just pick a frequency, pick a distance, find what our alpha and beta values are, right? Because that's our first step. So anyway, that's where all of this shenanigans is going. Now, something out of this paper that's interesting, right? So, is what do we pick for L naught? I initially was going to take L naught to be like the median value of all my losses that I have available. Maybe L naught is just 0. Right? There's no reason why L naught has to be anything besides 0. So maybe this becomes, and so this is what I'm thinking about what we were talking about before. So if L naught is 0, maybe we take this instead as that integrated derivative. Right, so now this becomes the integrated over alpha, of course, if you remember, by dl dei x minus xi, right? Maybe we do that times alpha. Maybe that's the best way to get it, because that'll give us our value there, or that'll give us, right? So what we're going to do is that'll give us our importance metric for each of these environmental components E sub I, right? So like F10.7, AP, all these metrics for specific environmental factors. So then what we're doing is we're multiplying our metric for the importance of the environmental factors by our fit parameter beta. Maybe that's how we do it. That might be the best way. But I want to take a look further into this paper. Oopsies. Ah, damn it. Oh no, my coffee is almost out. What am I going to do without my coffee? No coffee, no life. Whoopsies. I hit a button. Sorry. Nope. Damn it. There we go. Okay. Okay. So all right, so we can ignore the deep lift thing. Let's see what their unified framework is. And then that'll be the last section, I think, of this. Because I think we'll have our change metric, which is kind of what we're looking for, right? Okay, so unified framework. Gradient star input and integrated gradients are, by definition, computed as a function of the partial derivatives of the target output, right? In this section, we will show that epsilon LRP and deep lift can also be computed by applying the chain rule for gradients. If the instant gradient at each nonlinearity is replaced with a function that depends on the method. Okay. All right. Does that really matter for us? We're saying there's only a single layer. I don't know if that matters for us. Right? Because that's just going to end up, it should end up just collapsing into one of the two methods. Right? Because we're going to be summing over our layers. So it's just going to end up being... Okay, so let's see what they say. Let's see what they say. Okay. Proposition 1. So let's look at propositions 1 and 2 because these are for the two different methods. Proposition 1, epsilon LRP, so the first of the multilayer, is equivalent to feature-wise product of the input and the modified partial derivative, which equals G LRP, equals Fi Zi over Zi, i.e. the ratio between the output and the input at each nonlinearity. Xi. Okay. Hold on. G. Okay. But if this is just a single one, the ratio between the output and the input. So what do we mean by that? Is the output the input at each layer? Is that what it's talking about? Okay. This is what happens when you skip and you don't look at all the stuff. Okay, so we say in a deep neural network, each layer performs a linear transformation, right? So yeah, each layer is okay. Is followed by a nonlinear mapping. Oh, okay. So it's happening in the neural network at each layer, right? We're taking our input, right? We are manipulating our input through a linear change. So we're gonna stretch it by some value, and then we're gonna move it, right? Because we're stretching it and then we're moving it. And then we're gonna do between layer 1 and layer 2, we're gonna do some nonlinear function, right? So this is F. And then we're going to apply this nonlinear function to our linearly changed array or linearly changed vector and then apply it to the next one. Okay. But do we know what that is? And is that directly connected to what we're doing? What would be the nonlinear versus the linear piece? I'm not sure that there's a direct equivalence to this mapping, but I'd have to think about it with what we're doing. Okay, proposition 2, deep lift is equivalent to a feature-wise product, x minus x bar, and the modified partial derivative, the same. Okay, so he's just saying, or what these authors are saying is, we're just going to use this modified partial derivative mechanism, where we're defining that okay, so derivatives the weights across each. Okay, yeah, this we don't actually care about this. All right, because this has to do with the weights that you're applying to each of these things, and yeah, so this is really an interlayer mechanism that we don't care about because we're not actually doing that. We're just doing the single thing, right? Okay, okay. Um, all right, but. I think the good thing that we got out of this is I want to compare these two. So in my code, as I move forwards, what I'm going to do is I'm going to compare both of these and look at how that affects the error as I go through, right? So going back to my model. Going back to my model. This DLDE we're going to use both the gradient star and the integrated gradient, right? And we're going to try both of them. We'll try them. We'll see how that affects our error as we go through. And then we will just kind of select the best one. We'll just do a guess and check. We'll see. Does this one work better? I don't know. Does this work better? Hey, that one works better. We're going to use that. We'll figure the explainability about it later. Oh, man. Okay. So I think what we've done here is we've found a couple of tools to apply to give myself more work to do. Yes! We love giving myself more work to do because I don't have enough work and I'm cranking through my work way too fast. Clearly, that's what's going on. In no way is the exact opposite of that true. At any rate, so I believe that is where we're going to call this paper here. Because again, today was just sort of a, I was abusing the fact that I have a stream to actually push my research project forward. So all of you got to be just witnesses to me messing around and trying to figure out stuff for my work. You were all pawns in my game. Anyway, so I'm gonna call that for today's Sunday morning paper. Next Sunday, I think we'll go back to a philosophy paper. Unless I can find a cool video. What I will do, I will put it out if I can find another cool video like I did with the animators verse math and animator verse physics. I'll do that. Otherwise, I'll do a philosophy paper as something different, right? To just sort of switch things up. I checkmate myself in 10-dimensional chess. That's how it works. I try and play these things and then I end up just crashing, burning. It's great. It's a lot of fun. Anyway, so yes. So next Sunday, we will be doing a philosophy paper unless I find a really cool video, in which case we'll watch the really cool video and talk about it. Our next actual stream is going to be Tuesday for our evening stream. As always, Tuesday evenings are our kind of relaxing, do something different streams. We will read a chapter of The Hobbit and maybe a short story. I think that's what we'll do on Tuesday. And then Thursday is going to be more researchy kind of work. We're going to dip our toes back into the path integration stuff on Thursday. However, I will say, I'm going to say this here, and it's going to be on my schedule when I put that out. Thursday, we are going to move our stream to the evening, specifically this coming Thursday, just so I can give myself a little more. Actually, you know what? I have to move it to the evening regardless because we have to bring dog to his surgery on Thursday morning. So yes, so Thursday is going to be an evening stream. Exactly what time I will figure out, and I will post up in my schedule. My schedule will go up on the Discord, which is not visible right now. Gee, I'm such a horrible streamer, man. Where's my Discord? Discord status should be on top. There we go. There's our Discord status, or our Discord up there. It's also in the description below, in the information below. But there's the Discord link. I will put up the new schedule in the Discord. Also, I will try to remember to actually ping my Discord to say, "Hey, I'm going live," which is something I should, do as a streamer. But anyway. So thank you all for hanging out for this hour and a half of absolute insane math. It's kind of interesting to see how some of these things work. Like I said, I don't really have a background in machine learning, deep neural network type things, but it's cool to see how some of these things, you just get a view into how some of these things like the large language models work, or how we try and figure out how they work. Because that's the whole problem with them, is they're black boxes. We don't actually know how they work, which is fun. At any rate, yes, thank you for showing up today. I'm going to see if there is another physics streamer going on. If there is, we will raid them. So let's browse and take a look at science and technology. Let's see if anyone's doing any mathy fun things. Oh, there's a NASA video. That's just a video. I want someone who's actually doing some shader coding. That's us. So we're up there with 8 viewers. Is anyone doing any math? I don't see anyone doing any math. All right. Geez, I don't know, man. I don't see anything that's really worth hopping into here. Most of these are like automated streams. That's silly. That's kind of silly. Here's someone who is talking with a science writer about her book, How Evidence Shows What Reality Works. Sure, why not? Let's read them. So we're going to do /raid NERDUINO, right? And Nerduino? NERDUINO. All right, there we go. So again, thank you guys for showing up. I don't know what to talk about, but enjoy. We're gonna go over and raid. Bye. Kablow.